One of the major uses for polynomials is that you can use polynomials to approximate other function values. What kind of function values? Well, how about something like sine, right? We know this graph of sine looks like this, but if someone said, I want to estimate a sine value because I really need it, how are we going to do that? The sine is just a y value on a unit circle, right? So, I mean, how well can you estimate a y value on a unit circle? Well, around 1700, a mathematician found a way of writing down a polynomial for each function that better and better estimates those function values. Now, in pre-calculus, we're not going to see how he came up with a polynomial, but you will see that there's a pattern. We can certainly continue the pattern if we had to, and you can see actually how good the answer is. So this is the function he did. How about if I call it the y? I'll call this f of x, and I'll call this one g of x so I can make it a table at the very end. He started with x in the case of sine. Now, x doesn't look at all like sine. It does really close to 0, though. If you don't go too far away from 0, y equals x and y equals sine look a lot alike. Now, what he put in next was minus x cubed divided by something that's very strange looking. He wrote 3 factorial. Now, what is 3 factorial? If I go over here and put 3 factorial, Desmos tells me that's 6. The real definition of 3 factorial, and you should have seen this in college algebra, is 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. We don't want to have to write all this and in that mathematician's formulas. We can do with this just fine. So at any rate, what's happened so far? A cubic does look like this. And you can see that it actually hangs with sine all the way to the peak. If I add another term, and these terms usually alternate, this is x to the 5th. I want to get out of there. I want to divide it by 5 factorial. And you can see we're now get a polynomial which actually stays with sine past the peak and down the slope a little bit. The next one's supposed to be a minus, so this is x to the 7th divided by 7 factorial. Looks like that. We now have a polynomial that stays with sine all the way through the first hump. Okay, we can now see the pattern, right? We can see that this goes minus, plus, minus, plus. All the powers on top are odd powers. That makes sense, by the way, because sine is an odd function. This is actually why sine is called an odd function. Yes. Anyway, so I want to put x to the 9th, and I want to divide by 9 factorial. And now we have something that almost gets down to the bottom. The next one needs to be a minus, just following the pattern. Not explaining the pattern, we're just following the pattern. I want to divide by 11 factorial like that. And we now get something that almost gets down to the bottom of the hump. And I'm going to keep with the pattern. This is going to be x to the 13th divided by 13 factorial. Looks like that. We now get a function that goes past the peak. I'm trying to get over to 2 pi. I'm going to go, let's see here, minus x to the 15th divided by 15 factorial. And we get something that almost makes it all the way to the edge. Let's add one more term. Plus x to the 17th. Oops, not like that. Like this. Divided by 17 factorial. And if we just go from 0 to 2 pi, you can see that the graphs are almost identical. Let's go change the window a little bit. Just going from 0 to 2 pi. Like that. Let's just look at the part of the graph we find interesting. Right? That's not the graph of sine. That's the graph of sine along with the graph of this very long polynomial. Now, you might not like the very long polynomial, but on a computer, which is, by the way, this is what your computer does to estimate sine values, the graphs are almost identical, which is really good. And the fact that sine is periodic means we can pretty much find the sine of anything by bringing it back between 0 and 2 pi and finding this estimate of the y value. Now, if you want to know how good this estimate actually is in this case, I'm just going to go to a little table. I'm going to make y1 f of x1. I'm going to make this one g of x1. And let's just plug in some numbers. For example, if I plug in 1, here's what the computer estimates as the sine of 1. Here's what the polynomial estimates as the sine of 1. And like I say, the thing about the polynomial, that's just arithmetic, right? It's not horrible, hard stuff. It's coming up with a polynomial is kind of cool, and you do that in Calc 2. But here it's not so bad. If I try to plug in another number on the table, let's see, well, let me put in another number. How about 2? 909, 29743. It's at 2, it's still actually lining up to 8 decimal places. If I put in 3, we finally get a little bit of difference. Now, when we created this polynomial, we saw, by the way, that it got very close to the values very early on, and it took a lot more terms to actually add before we were actually getting a good estimates over here. So I'm thinking that the further away I move from the origin, the worse these estimates are going to get. Let's see here. If I just plug in 4, you can see they're still really close. They're differing in about the 6th or 7th decimal place now. If I put in 5, they're still really close. They're now differing in the 3rd or 4th decimal place. I guess it's the 4th. But it's still really close. This is exactly what your computer does to estimate the values of sine. And this is actually one of the big, most important reasons that polynomials are important, is that someone comes up with a function, we can try to find a polynomial whose function values are very close to the original, and then just plug into the polynomial instead.